Studio microphone intro. The fear of too much knowledge. There are moments in human history when we come dangerously close to understanding too much. Moments when technology doesn't just answer questions, it starts asking new ones. And sometimes, those questions are far more terrifying than the answers. In 2019, a machine quietly powered on inside a lab. A machine unlike anything humanity had ever built. Google Sycamore, a quantum computer, designed to perform calculations so complex that even the world's fastest supercomputers would take thousands of years to complete them. And for a brief moment, it worked. It didn't just succeed. It shattered expectations. But what came next was not a breakthrough headline. It was confusion. Because the deeper researchers looked into the results, the less they understood them. Studio Microphone Part 1. What quantum computers really do. To understand what happened, you need to understand something simple. Classical computers, like your phone or laptop, think in bits. Zeros and ones. On or off. Everything you see, every video, every app, is built on that simple logic. But quantum computers are different. They use something called qubits. And qubits don't follow normal rules. They can be 0 and 1 at the same time. A concept known as quantum superposition. And when multiple qubits interact, they create something even stranger. Quantum entanglement, a state where particles become connected, no matter how far apart they are. This isn't theory. It's real. And it's been tested, again and again. Studio Microphone Part 2. The moment of quantum supremacy. When Sycamore was activated, Google ran a specific experiment. A task designed to prove one thing: that a quantum computer could outperform any classical machine on Earth. And it did. In just minutes, Sycamore solved a problem that would take traditional supercomputers thousands of years. This moment became known as quantum supremacy. It was a turning point. A signal that humanity had crossed a technological threshold. But here's what most people don't realize: the problem Sycamore solved wasn't useful. It was random. A test. A demonstration. Because the real goal wasn't speed. It was understanding. Studio Microphone Part 3. Where things get unclear. After the initial success, researchers continued experimenting. Pushing the system further. Running more complex simulations. Testing deeper layers of quantum behavior. And that's when something interesting happened. Not terrifying. Not supernatural. But confusing. Some outputs didn't match expectations. Not completely wrong, but not perfectly predictable either. Tiny deviations. Statistical anomalies. Patterns that were difficult to explain with existing models. Now here's the important part. This doesn't mean the machine was thinking. It doesn't mean it was communicating. It means something far more realistic. We don't fully understand quantum systems yet. Studio Microphone Part 4. The human problem. When humans encounter something they don't understand, we do something dangerous. We fill in the gaps. We imagine intention. We imagine meaning. We imagine patterns. This is how myths are born. And in the case of quantum computing, this is how rumors start. Stories began spreading that the machine generated messages, that it created unknown symbols, that it was interacting with something beyond reality. But there is no verified evidence of that. What actually happened is more subtle. And in many ways, more fascinating. Studio Microphone Part 5. Why quantum results look weird. Quantum systems don't behave like normal systems. They are probabilistic. Which means they don't give one answer. They give many possible outcomes, with different probabilities. So when you run a quantum computation, you don't get a clean result. You get a distribution. A pattern of likelihoods. And sometimes, those patterns look strange. Unexpected. Even structured. But that doesn't mean they are messages. It means our interpretation is limited. Studio Microphone Part 6: The Role of the Observer, Extended. Here's where things stop feeling like science and start feeling like philosophy. Because in quantum physics, the observer matters. Not metaphorically. Not symbolically. Literally. The act of measurement changes the system. This idea comes from one of the strangest principles ever discovered in science: observer effect. At the smallest scales of reality, particles don't behave like solid objects. They exist as possibilities. Waves of probability. Multiple states, all at once. Until they are observed. And the moment you measure them, those possibilities collapse into a single outcome. Think about that for a second. Reality, at its most fundamental level, is not fixed. It becomes fixed only when it is observed. This isn't science fiction. This is tested. Repeated. Verified in laboratories across the world. Now imagine what that means for a machine like Google Sycamore. A machine designed not to observe reality from the outside, but to interact with it at the deepest possible level. Not just measuring particles, but manipulating their states. Exploring combinations that human intuition cannot even visualize. Of course the results would look strange. Of course they would feel unnatural. Because we are not built to understand a world where something can exist in multiple states at once, where outcomes are probabilities, and where observation itself changes reality. So when people look at quantum results and say, "This doesn't make sense," they're right. But not because something is wrong. Because something is deeper than we expected. Studio Microphone Part 7: Did Google shut it down? Extended. Now let's address the part that fuels the most fear. Did Google shut down Sycamore because of something terrifying? No, that's where the story gets twisted. Quantum computers don't work like normal machines. They are not always running. They are not always active. They operate in controlled experiments. Short bursts of computation, followed by calibration, adjustment, and redesign. Because quantum systems are extremely fragile. Even the smallest disturbance, temperature changes, vibrations, electromagnetic noise, can affect the results. So when a system is powered down, it's not a shutdown. It's part of the process. Part of refinement. Part of progress. But from the outside, it looks like silence. And silence creates speculation. People assume something is being hidden. That data is being locked away. That truth is being suppressed. But in reality, what's happening is something far more ordinary and far more important. Science takes time. It takes verification. Peer review. Repetition. And until results are fully understood, they are not released. Not because of fear. But because of responsibility. Studio Microphone Part 8: What about Michio Kaku? Extended. Then there's the name that often appears in these stories, Michio Kaku, a respected physicist. A communicator of science. Someone who has spent decades exploring the boundaries of human knowledge. He has spoken about quantum computing. He has described it as revolutionary. As powerful. As something that could change the world. And he's right. But there is no verified evidence, no real statement, no confirmed event, where he witnessed anything like messages from beyond reality. That version of the story is built for impact. For clicks. For views. For emotion. And it works. Because it taps into something deep inside us, the idea that we might discover something we were never meant to find. But real science doesn't work that way. It doesn't jump to conclusions. It questions everything. Even its own results.